Well, I was born in Fort Wayne, Indiana, and my coming to Huntsville is really serendipitous. It's a matter of being at the right place at the right time and a number of events. In high school, I had already planned my career. I was going into the nuclear field because that was the new kid on the block. It was an exciting, challenging thing to do. With 3 other sophomores in high school, we decided it would be a neat thing to do to build an atom smasher. So with the support of our physics teacher and the cooperation of the principal, we got approval to build a cyclotron in the basement of the school. Of course, that would never happen today, but nevertheless, we were fortunate in that regard. When we graduated, it was not operational yet, but that was carried on by students for several years. So I did my undergraduate work in physics and chemistry at Purdue University and graduate work at the University of Minnesota. During my tenure at Purdue University, again, I was very fortunate to get a job, well, almost a dream job, with the General Electric Company, working on a project for the Atomic Energy Commission and the U.S. Air Force. In the Cold War days, there was a desire to have a bomber that you could keep up indefinitely, like a nuclear submarine. So we were building a nuclear-powered bomber. That led to my ultimately coming to Huntsville because that project was canceled early in 1961, just as the lunar program was being approved. So I was fortunate to come to Huntsville and interviewed and was given a job by Bill Lucas in the materials organization. So from that point on, I worked on all the materials for the development of the Saturn booster. And actually, I was chief of the projects office in the materials group. So that got us involved in everything that was going on, not just Saturn, but all the other projects. It was our job to coordinate the materials research with the designers to make sure that they had the materials that they needed in order to build and design and build the hardware. While I was in graduate school at the University of Minnesota on October 4th, 1957, I came home from school to hear on the news that the Russians had launched a satellite. This somewhat irritated me because I'd had my undergraduate work in physics. I was in graduate school of physics, and nobody had ever mentioned the possibility of an artificial satellite. So it turned out that Minneapolis was right on the flight path. So every 90 minutes that night, I went out and watched Sputnik come over. Immediately, that didn't have an effect on my career, but ultimately it did. As I say, when the project I was working on for the Atomic Energy Commission and the Air Force petered out, my next emphasis, of course, turned to space because that was the most exciting and challenging job on the market. And I was very, very fortunate to get a job here at the Marshall Space Flight Center. In fact, when I meet and talk to children today, they often ask, well, what classes did you take? How did you prepare for a job on the lunar program? Well, you can't, because there was no such thing. And the reality today is that a large number of the children are going to end up in jobs that do not even exist today. So I try to encourage them to get a very good, solid, broad background to take advantage when these things come along. But in those days, the stimulus of the space program and the Manhattan Project and other things that were going on had a dramatic effect on education. If you look at the history of just, say, graduates with advanced degree or PhDs, there was a huge spike in the 60s. And of course, unfortunately, it dropped off in later years. So the programs like the Apollo program, like the Manhattan Project, stimulated interest in research and education in not just those particular areas, but across the board. We had to either re-qualify existing commercial materials for the more severe environments that we were going to experience, or create new materials, and we did, particularly in the engines, because of the temperature extremes, the vibrations, and all of the actions that are going on. There simply were not materials that were strong enough, had the high temperature capability that we needed. So we invented a lot of new materials. Very simple things like you, you can't use WD-40 as a lubricant in space, so we developed solid film lubricants. Of course, we use solid film lubricants in everything today. So it was like that in every area, that even though there were materials that we used, that we had to requalify them. And that entailed a great deal of work. It necessitated our working with the ultimate suppliers of the materials to stabilize the specifications so that we knew we were going to get the same material with every batch that came in. There was also the necessity to develop techniques for evaluating the materials, both as we receive them and then after they've been used, and particularly when we had failures. Failure analysis is something people don't think about, but I think that's one of the major accomplishments of the Apollo program. When you stop to think that you got a vehicle with 3 million parts, give or take some, and you have a failure, and you're trying to figure out what went wrong, particularly when you can't get the hardware back, it is a real challenge. And there was not any real disciplined approach to failure analysis when we started, but we developed failure mode effects analyses. We developed all the techniques that are common today to allow us to evaluate and pin down what actually the causes were. So there are many attributes of the materials area that people don't think about. Let's say failure analysis is one of them. Another one is non-destructive testing. There's 20 miles of welds on the launch vehicle. We x-rayed every inch of those welds. And the x-rays in those days, the old folks will remember going to the dentist and getting little x-ray films of their teeth. And that's what we used to x-ray 20 miles of welds. And technicians went over every inch of those x-rays looking for defects, and we had to then fix them. Among other things that nobody had ever encountered, when we went to hydrogen fuel, hydrogen has such a very, very small molecule that it'll get through the smallest of defects and the smallest of cracks. So you had to have a perfect weld. Nobody had ever made welds of the length and the quality that we needed for the launch vehicle. So we had to not only develop the materials, we had to develop the welding techniques, the inspection techniques, the casting techniques, all of the things from beginning to end. That was a major challenge, but it was a very interesting challenge. Well, say having to make 20 miles worth of welding on a vehicle was a tremendous challenge. Among other things, when you had things like a bulkhead, the weld land changes from maybe 1.25 inches down to maybe 5/8 of an inch. So it's constantly changing, causing the welding head to have to adapt to that change. We had to develop all new welding equipment. We had to develop backup bars in order to get the cooling in order to get the right temperatures for the welds. This entailed a great deal. We continued to develop welding techniques and welding machines to the point that 20 years ago we developed what's now called friction stirred welding, which is now being used on the latest vehicles. So the whole process was to try to get the best quality weld with putting the least amount of heat in the minimum amount of time. Okay, well, the Saturn and Saturn IB kind of get ignored when we talk about going to the moon, but they were a very, very important part of it. The reality is, in 1961, all we had were little ballistic missiles like the Redstone and the Jupiter. We had nothing large enough to put the service module and the command module into orbit to develop it. So the Saturn I was kludged together by using a Jupiter center tank and then 8 Redstone tanks around it. And then we took the largest engine in the world, which was a Titan engine, but it wasn't big enough, so we had to upgrade it, and we had to put 8 of them on the vehicle to get us 1.5 million pounds of thrust. Had we used those engines on the Saturn V, there would have been 40 engines on the first stage. Well, it's hard enough to get 5 of them started, let alone 40 of them. And the transition, or the upgrading from that size engine to the F1 engine was a major problem. As we talked earlier, we had to develop new materials. The whole thing was a mystery. Much of it you couldn't analyze, so we had to learn a lot by test, and we blew up a number of engines learning those lessons. Unfortunately, the Saturn I and IB kind of get ignored in the whole history of things, but they were very, very important elements in our success in getting to the moon, both in terms of giving the astronauts time and space to really learn what they can do. We developed a lot of materials for this in the I and IB program that ultimately we used in the Saturn V, a lot of techniques. The insulation on the S4B stage, on that one, it was small enough we used an internal insulation. Well, of course, we used the S4B stage not only on the Saturn I, but on the Saturn V. That is an overlooked part of the program. And of course, even late in the program, we launched the crew to Skylab on a Saturn IB. So it was used, what would we have, something like 13 launches on each one of those. So they were very, very significant, very fundamental in our achieving the overall project. We had a vehicle being stacked at the Cape, and we were ready to ship the S4B stage from Huntington Beach, California. The last thing we do is an acceptance test firing. So we had the vehicle in the stand. Just before the engines lit, the whole stage blew up, wiped out the stage and the stand. We had to do a failure analysis of that by reconstructing the whole stage, piecing things together to trace down where the explosion started and how it was propagated. And it turned out in that case it was a very simple thing. A welder had used the wrong weld wire in joining the two hemispheres of one of the helium spheres that was used for pressurization and cooling, and that didn't have the strength that it should have, and it wiped out the entire stage. So very simple things can come back and bite you and cost a lot of money because, as I say, we wiped out an entire stage for that. Now, insulation was another really major headache. Liquid hydrogen has to be kept at 423 degrees below zero. We used, well, people always ask what's the vehicle made out of? Well, it's made out of aluminum, but that's just a superficial statement. There are many different alloys of aluminum that are used, and every material that went into that vehicle was picked and designed for that particular application. For the hydrogen tank, we wanted to use the highest strength alloy at liquid hydrogen temperature, so we used a material called 2014 aluminum. In order to take advantage of that strength, we wanted the hydrogen in direct contact with the skin, and that allowed us to use very thin walls. Since the hydrogen had to be kept 423 degrees below zero, it meant we had to put the insulation on the outside of the vehicle. Well, every time you tanked the vehicle, which we did over and over and over again before we ever flew it, the tank would shrink. It would shrink about 3 inches in diameter and 8 inches in length. But the insulation on the outside wouldn't shrink at the same rate. So we had to develop special adhesives and attachment techniques to hold the insulation on the tank. And even with that, due to the shrinkage, we would get microscopic cracks in the insulation that you couldn't even see them with the naked eye. But the next time you put hydrogen in that tank, it pumped air through the insulation, and you got frozen air on the skin of the tank. And then, say during launch, the friction due to the heating due to friction going through the atmosphere would cause that ice to sublime. It would go from solid to gas in one step, and it would blow divots out the side of the insulation. And then we had to figure out, well, how big a hole can you stand before the aerodynamics strip all the insulation off the vehicle? How do you repair it? And all of these things. There was far more that we did not know about going to the moon than what we did. And every day was a new challenge. You're facing questions that nobody had ever thought about before. And it seemed like every time you solved one problem, it created 3 more problems that nobody had ever thought about. So that was really a challenge, but it really was part of the excitement of the project, of dealing with this on a day-by-day basis. I think one of the most amazing opportunities that we had was working with the German team. Now, when people like myself came to work here, we were 20-year-old kids. The German team was probably 8 to 10 years older than we, and of course they were our mentors. But the important thing, there was never any we or they between the groups. We were working on one project, we knew what we had to do, everybody had the same job description, getting the same pay, and there was total harmony, if you will, in terms of dedicating oneself to accomplishing that objective. Today, for example, they teach systems engineering as a class in college. There was no such thing in that day. Everybody was a systems engineer, every single person. When you were working on a problem, you were thinking about what effect does this have on the guidance control? What does effect it have on this thing? What effect does it have on something else? And quite different than what I understand is done in some places today. We had a very efficient way of solving these problems. You got on the telephone, you called up everybody that you thought was involved, you got them in the room, and you sat down, you talked about it, and you argued about it, and you came up with a solution. And then you tried that. If it didn't work, you went to plan B. Everybody, as I said, was conscious of what everybody else's job was. The other thing is that for most applications, 96, 98% reliability is great. We had to have 100% reliability. And every decision that you made was a life or death decision. And you were conscious of that every single day. You were always thinking about if this bolt fails, or if that weld fails, or if something else goes wrong, what effect is it going to have not only on the crew, but on the people on the launch site and so on. That was, it put stress on everybody. But as I say, I think that also was a major contributor in the success that we had, because every one of the launches that we had was successful. Well, let's say every launch we had met the mission. We had problems. There were failures. Most of the people don't know about what those failures were, because we had enough contingency and enough thrust and control that we were able to compensate for them and still have a successful mission. Of course, I was involved in the launches of the Saturn I's and the Saturn IB's because we were developing certain payloads. I will never forget one night that we had a launch about midnight. It was a perfectly clear night, not a cloud in the sky. When we lifted off at midnight, of course, it was just like daylight. But the most amazing thing is that you could actually see the S-4B stage burn into orbit over Africa with the naked eye. And that was an amazing experience. I was doing my part as part of the flight readiness review for the first Saturn launch, Saturn V launch. When I got done, Dr. von Braun says, you're going with me to the launch site and tell me whether the criteria that you've just set out here are being met before we launch. So I was part of the team for the very first launch. It was November 7th, 1967, 7 a.m. approximately. But that was quite an experience. Frankly, I don't think that there was a dry eye in the control room. It was like sending your child off to school. I mean, we'd worked on this thing for 7 years. Now here was the final test, go or no go. And with the liquid rockets, they lift off very, very slowly because of all the mass and the building up of speed. It looked like it was never going to clear that launch tower. And everybody was kind of helping it along. But of course, that was an extremely memorable event to see that first vehicle lift off and basically prove the success of all the things that we had done for all of those years. And I frequently get asked, well, what were you doing during the what were you doing during Apollo 11? Well, we were quite confident that the vehicle was going to work for that. So my answer has always been, we were working on 12 and 13. It was another launch. We were confident it was going to work, but our problem was we had another vehicle coming out to the launch pad, and we had to have it ready. So our focus was really not on Apollo 11, but on the downstream launches. Well, as I said, I was born and raised in Yankee land in Indiana and was working in Ohio. I had certain trepidations about coming to Huntsville because the racial issues were quite prominent on the world press. But frankly, NASA and the Department of Defense had a very major influence on Alabama's response to that problem. It didn't take too long for the state leaders to recognize that all the money coming into the state of Alabama was coming in because of these programs. And as a result of that, there was more of a receptivity to follow the national objectives and desires to resolve this issue. And the leaders recognized that if they didn't go along with it, that money was quite likely was going to disappear. So I was here at a time where I could see the shift in the attitudes about race relations. Fortunately, Huntsville has always been a very cosmopolitan city. You know, people from all over. As a result of that, I would say that we had little or no real racial issues in the city of Huntsville. When the schools were integrated, the public were out there supporting it. Even though there were police all over the place, it was the public that was there escorting the children into the schools. Not to say that there weren't some issues and problems, absolutely there were. But compared to other places in Alabama, Huntsville was spared the problems of integration that other places did experience. So certainly the presence of the federal programs here in Huntsville not only helped North Alabama, but it ultimately led the state of Alabama into trying to resolve these issues perhaps sooner than they might have done otherwise. With Congress cutting off the funds for the Apollo program, Marshall was in a very desperate situation. After all, our whole business was smoke and fire. If you don't have any payloads, if you don't have any missions, you don't need launch vehicles. So this was a very difficult time, and the center was very, very bright in recognizing we had to do marketing. And of course, Bill Lucas was put in charge of this new marketing organization called Program Development. And it was our job to look at what areas can we imply the expertise of the center in order to attract new business here. Out of that, of course, came Space Shuttle, ultimately Space Station, the large observatories, and also our getting involved more into the operational end of the business rather than just building the hardware. So that became a very significant effort. I was fortunate after we began to get the approval of some of these programs. Of course, I went on to become a project manager in the Space Shuttle program, and then, of course, many other things. Really, I went from there into project management. So the future of the center really hinged on the work that came out of the program development activity. It was a new experience for us. We never had to sell ourselves before. We never had to go out and market. As soon as somebody said we have a payload, Marshall Center was going to get it into orbit. So now we had to go out and really sell ourselves. I have worked on more projects that have been canceled than most people have ever thought about working on. So I'm quite familiar with that aspect of it. But yes, we did look at the fifth stage Centaur, but found out that we had enough reserve, enough capability in the launch vehicle. We didn't really need that. But there were all kinds of programs and projects that we were looking at. One of the most disappointing things is in the 70s, we had laid out a complete plan for going to Mars. We had designs of the hardware that we thought we might need in going there. We laid out schedules. We laid out budgets. We laid out the concepts of how you stage in getting to Mars. And unfortunately, it never got off the drawing board. Interestingly, as I said, I'd been working on an aircraft nuclear propulsion program, so when I came here, the first project that I was working on, was a nuclear stage to go to Mars. Dr. von Braun was very, very perceptive. And in the Space Act of 1958 that created NASA, there is a paragraph in there that we will develop a nuclear stage to go to Mars. Well, unfortunately, the interest dropped off. But yes, there were a lot of false starts. There were a lot of things that we looked at and either decided that really wasn't the right time to do it, or more generally, we couldn't get the financial support to undertake it. There is no question that the Apollo program was a political victory. But the real value of that program is all the technology that we had to develop to accomplish the job. We today are living off of the technology of the 60s. Not only did this come from the space program, but the space program stimulated technology development, experimentation, scientific endeavors across the board. And that is what we are living on today. Now, I had an opportunity to be invited to be an advisor to the European Space Agency, so I spent almost 3 years in Europe working with them. And frankly, I don't think there's any question that I learned things that are more important than anything I taught them, and probably the most important thing is the only thing that this country has to sell on the world market is technology. In the first place, the third world countries are catching up with us. In the second place, there is no program in this country today driving technology like the programs in the past. And that is, it forebodes real problems for us. Among other things, this country needs to commit to a very high-tech, challenging program like going to Mars. Putting people on Mars will open the fields or open our knowledge to all kinds of science. But just the technology to get us to Mars and back will fuel our economy for another 75 to 100 years. And we look at it from the standpoint, or I look at it from the standpoint, by not doing this, we are cheating my great-grandchildren. Because we are living off the technology 60 years ago. And it is so important for our future that we once again take on significant challenges. Yes, they're expensive. There's no question about it. But the payback from this is incalculable. We barely scratched the surface of what we could and should learn by going to Mars. It's a no-brainer. The moon ought to simply be a stepping stone to Mars. We can learn a great deal. There are things that we know the composition of the moon. We can mine certain things. We know there's water there that can be used for habitability, that can be used for hydrogen and oxygen fuel. Because of the gravity, it takes a much, much smaller rocket to go to Mars from the moon than it does to Earth. I mean, there's no atmosphere, so you can study the space radiation effects on materials and on people. I say it's a no-brainer that we ought to use the moon as a stepping stone. And if we're willing to stop our curiosity and our exploration 250,000 miles from Earth, then we're not really living up to our potential. I mean, we got a whole solar system out there, we got a whole universe out there, and the moon is just the first step.